Hello everyone, welcome to module 9. So in this module we're going to talk about heat. So in this we're going to discuss temperature and thermal equilibrium. We'll try to define heat and we'll try to understand changes in temperature and phase. So let's start with section 1, temperature and thermal equilibrium. In this lecture we're going to try to relate temperature to the kinetic energy of atoms and molecules. Describe the changes in the temperatures of two objects reaching thermal equilibrium. Identify the various temperature scales and convert from one scale to another. So let's start with defining temperature. How do you define temperature? So temperature is the measure of the average kinetic energy of the particles in a substance. So adding or removing energy also changes the temperature. So one of the main ways we calculate temperature is the main concept is using the internal energy. So what is the internal energy? Internal energy is the energy of a substance due to both the random motion of its particles and to the potential energy that results from the distances and alignment between the particles. So there are three forms of internal energy. So the first one is translational. So an example of that would be to take an airplane in flight or a roller coaster at the bottom of a rise. So the microscopic example is a carbon dioxide molecule in linear motion. So this is a type of kinetic energy. You have rotational kinetic energy, which is basically concept of a spinning top, where you have a carbon dioxide molecule spinning about its center of mass. Again, this is also a kinetic energy. And you have vibrational energy, so where you have the macroscopic example is a plucked guitar string. And microscopic example is the bending and stretching of the bonds between the atoms in the carbon dioxide molecule. So this is the kinetic. So this involves kinetic and potential types of energy. So next, let's talk about thermal equilibrium. So thermal equilibrium is the state in which two bodies in physical contact with each other have identical temperatures. Again, remember this term, physical contact, meaning that they have to be physically in contact with each other for them to achieve that identical temperature. So by placing a thermometer in contact with an object and waiting until the column of the liquid in the thermometer stops rising or falling, you can find the temperature of an object. So the reason that the thermometer is in thermal equilibrium with the object is that because of the thermal equilibrium. So the main reason that it stops at a certain point is because thermometer reaches a thermal equilibrium with the object. Now, the temperature of any two objects in thermal equilibrium is always gonna lie between their initial temperatures. So let's take the example here. Let's say you have a glass of ice water, and you put it into you put a thermometer inside it. So what happens here is that the heat in the thermometer, so the heat in the thermometer, which is higher, is generally taken by the water, and both of them reach a certain temperature. So when both of them start reaching a certain identical temperature, there is no heat flow. So then when the heat flow stops, we say that that is the point where it has reached thermal equilibrium. So that's the point when it has reached thermal equilibrium. Next, let's talk about thermal expansion. So in general, if the temperature of a substance increases, so does its volume. So this phenomenon where temperature causes change in its shape is called as thermal expansion. So different substances undergo different amounts of expansion for a given temperature range. And this thermal expansion characteristics of a material are indicated by the coefficient of volume expansion. So, and this volume expansion is generally given by gamma. And gases generally have the largest values of this coefficient, and solids typically have the smallest values. So this is an expansion of this is an understanding of how thermal expansion works on bridges. So because bridges are built made up of metal, so there is a chance that they might undergo a certain amount of expansion or contraction to make sure that that does not destroy the bridge. So these type of wavy joints are made to make sure that if there is a contraction, so it contracts itself, and if there is an expansion, it expands itself, and there is movement on both sides. So therefore the bridge stays intact rather than undergoing compression or a tension. So these types of joints, wavy joints, are generally used for bridges and heavy roads to make sure that they do not undergo any damage due to temperature. So how do you measure temperature? So the most common thermometers generally use a glass tube containing a thin column of mercury, colored alcohol, or colored mineral spirits. When the thermometer is heated, there is an increase in the volume of the liquid, and that change in length is proportional to the liquid column, which is also proportional to the change in the length of the liquid column is proportional to the temperature. That thereby we measure the temperature. So we calibrate the length to that of the temperature to make sure that this particular values can be used to determine the actual temperature. Now, when a thermometer is in thermal equilibrium with a mixture of water and ice at 1 atmosphere of pressure, that temperature is called as the ice point or the melting point of water, and this is defined as 0 degrees Celsius. And when the thermometer is in a thermal equilibrium with a mixture of steam and water at 1 atmosphere of pressure, the temperature is called as the steam point or boiling point of water. This is about 100 degrees centigrade. Now we use 3 different temperature scales. So the first one is Fahrenheit or Fahrenheit. The next one is Celsius, and the third one is Kelvin. So all of them are characterized based on their points of the ice point and the boiling point. So for example, if you consider this to be the ice point and this to be the boiling point or steam point. So on the Celsius scale, so let's consider this as the Celsius scale, this as the Fahrenheit scale, and this is the, say, Kelvin scale. On the Celsius scale, this value is 0 and the boiling point is 100. So this is 0 degrees Celsius and this is 100 degrees Celsius for the boiling point. On the Fahrenheit scale, ice point comes at 32 Fahrenheit and the boiling point comes at 212 Fahrenheit. Next, at the final one, you have Kelvin scale. So this is degree Celsius, degree Fahrenheit, and Kelvin. On Kelvin scale, the ice point is 273.15 Kelvin and the boiling point is 373.15 Kelvin. So these are the 3 scales and the 3 points by which we can distinguish them. Notice that the ice point and boiling point are divided by 100 divisions, and Fahrenheit scale is divided by 180 divisions, and the Kelvin point is also divided by again 100 divisions. So it's easy to understand the relationship between degree Celsius and degree Kelvin. Kelvin. So degree Celsius, so any temperature X at degree Celsius is equal to, so any temperature in degree Celsius can be written as, any temperature in Kelvin can be written as the temperature in degree Celsius plus 273.15. So any temperature at Kelvin can be written as degree Celsius plus 273.15, or to write it easily, so we can write as temperature in Kelvin is equal to temperature in Celsius plus 273.15. Or if you want to write temperature in Celsius, that becomes temperature in Kelvin minus 273.15. Notice that they are still divided by the same number of divisions. The only thing that changes is the starting temperature. So when this is 0, this is 273.15. So we can write that value is 273. So we add 273.15 to get Kelvin values. Now, what is the difference? What is the relationship between temperature in Celsius and temperature in Fahrenheit? So we know that these are equal divisions. Let's consider a certain point where this is temperature in Celsius. That same point on the Fahrenheit scale, let's consider that as TF. So based on the idea that the length is actually the exact same amount, so over the total length, so which is going to be, so Tc minus T0 over 100 minus 0. So Tc minus 0 over 100 minus 0 is equal to Tf minus 32 over 212 minus 32. So that will give you Tc over 100 is equal to Tf minus 32 over 180. So Tc can be written as 100 over 180 times Tf minus 32. So 29, 25s and 29s. So with that you get Tc equals 5 over 9 times Tf minus 32. Or if you rearrange the equation for Tf, so you can solve it on this own. So push this side and push 32 that side. That gives you 9 Tc by 5 plus 32. So this is the relationship between the temperature in Celsius and Fahrenheit. Fahrenheit differences between the temperatures. So these are the formulas that we can use. Now, the only difference between these scales of temperatures is that Celsius and Kelvin are a relative scale. So the common temperatures that are used as Fahrenheit, Celsius and Kelvin. So the only difference here is that the temperature values are something different. So temperature values in Celsius and Fahrenheit can be positive, can be negative, and also zero. So because the kinetic energy of the atoms is in the substance must be positive, the only scale that shows you the absolute temperature, the measured temperature in the absolute temperature, it should be proportional to that energy, should be positive also. So which means that a temperature scale with only positive values is suggested by the graph on the next slide, so which is going to be the Kelvin scale. So as the temperature reduces, you also notice that there is a reduce in the pressure, which is also the energy showing the energy as well. So which means that at some point it stops and becomes zero. That point is called as the absolute zero temperature. So this point right here is called as the absolute zero. So absolute zero here refers to the temperature where there is nothing negative or there is nothing below that. So that value is generally measured using the Kelvin scale. So that's why Kelvin scale is used as an absolute temperature scale. So Kelvin scale is generally written in uppercase T and it's generally called as the absolute temperature scale. So this is called as the absolute temperature scale. So that's why you get negative 273.15 degrees centigrade becomes equal to 0 Kelvin. So again, what are the common examples of Fahrenheit use? The ice point in Fahrenheit is 32 and steam point is 212. Applications are generally in meteorology, medicine, and non-scientific uses mostly in the United States. And you have Celsius, which is ice point is 0 degrees centigrade and steam point is 100 degrees centigrade. Applications involve meteorology, medicine, and non-scientific uses outside the US and other sciences internationally. And you have Kelvin scale, which is the absolute scale, which gives you ice point at 273.15 and steam point at 373.15. Applications involve physical chemistry, gas laws, astrophysics, thermodynamics, low temperature physics. So scientifically, mostly used scale is the Kelvin scale. So that is the end of temperatures. So let's go into the next section. So this section we're starting with defining heat. So the objectives here is to explain heat as the energy transferred between substances that are at different temperatures and relate heat and temperature change on the macroscopic level to particle motion in the microscopic level, and finally apply the principle of energy conservation to calculate the changes in potential, kinetic and internal energy. So let's start with heat and energy. So heat is simply the energy in transit, which means that it is the energy transferred between objects because of a difference in temperatures. So heat is only going to apply when there is a difference in temperature and there is not going to apply under any other circumstances. So heat is only transferred when there is a difference in temperature. So from a microscopic viewpoint, energy transferred as heat tends to move always from a high temperature to an object at low temperature. Now the direction in which the energy travels as heat can be explained by the atomic level. So how can we do that? So let's take an example of a juice in a can at a temperature of 45 degrees centigrade being dumped into water at about 5 degrees centigrade. Now, when you look at it microscopically, you start noticing that you have molecules that are continuously vibrating. So this vibrating molecules continuously hit the can, and the can transfers the energy directly outward into the water molecules, which results in the water molecules continuously randomly moving around each other and randomly having collisions. So as there is continuous transfer of kinetic energy from the internal molecules to the external molecules, at some point this continuous transfer of energy stops, and that is the point where we call it as thermal equilibrium, where the water tends to completely increase in temperature and the juice tends to decrease in temperature. So which means that there is a transfer of energy from a higher temperature body to a lower temperature body. So next, let's talk about the atoms of all objects. So generally are in continuous motion, and all objects have some amount of internal energy. Now, temperature here is a measure of that energy. So all objects have always some temperature. Now, heat on the other hand is the energy transferred from one object to another because of the temperature difference between them. So when there is no temperature difference between a substance and its surroundings, there is no net energy transferred as heat. So just as other forms of energy, you can also have a symbol that identifies them. So we use for PE for potential energy, KE for kinetic energy, U for internal energy, and W for work. Heat is generally denoted by the symbol Q. So because heat, like work, is also energy in transit, so all heat units are generally converted to joules, which is also the SI unit of energy. So heat units, you have joule, which is the SI unit, which is about 1 kg meter square per second square, which is the SI unit of energy. The next unit is calorie. Calorie is about 4.186 joule. It's the non-SI unit of heat and found especially in older works of physics and chemistry. You have kilocalorie, which is about 4,186, so which is 4186 joules, which is the non-SI unit of heat. You have calorie or a dietary calorie, which is also equal to 1 kilocalorie, which is used as a food and nutritional source of information. You have BTU, which is the British thermal unit, which is about 1055 joules, which is the English unit of heat and generally used in engineering, air conditioning, and refrigeration. You have therm, which is about 1.055 times 10 to the power 8 joules, so which is about 1055 megajoules, and it equals to about 100,000 BTU, and it's generally used to measure the natural gas usage. So next, let's talk about thermal conduction. So conduction here, the type of energy transfer that is due to the atoms transferring vibrations to neighboring atoms is called as thermal conduction. And the rate of thermal conduction generally depends on the substance. And there are two other mechanisms of transferring heat. One is convection, and the third one is electromagnetic radiation. So when you turn on a burner and the skillet handle heats up because of conduction, because there is a heat transfer from the burner onto the skillet to the handle. So these are the three forms of energy. Let's take into consideration each and every form of energy. Now, when you're driving the car, as you're driving the car, you have hot air molecules, so striking the window, so striking your car, which results in conduction, and the air results in, the hot air molecules continuously hitting your car results in convection. Now these molecules are going to be transferred from one part of the car to all parts of the car. That part is conduction, and the last part is the heat. Due to the heat comes from the sun, which also heats up your car, which is the form of radiation. So these are the three forms of heat transfer. So conduction, convection, and radiation. Next, let's talk about conservation of energy. So if changes in the internal energy are taken into account along with the changes in mechanical energy, so the total energy is universally conserved property. So which means that the sum of changes in the potential, kinetic, and internal energy must be equal to 0. So we can write the conservation of energy equation as delta PE plus delta KE plus delta U equals 0. So the change in potential energy plus the change in kinetic energy plus the change in internal energy must be equal to 0. So let's take an example. So an arrangement to the one used in to demonstrate energy conservation. You have a vessel that contains water. You have paddles that are propelling the water by falling masses turn into water. This agitation of the water increases its internal energy. The temperature of the water is then measured, giving an indication of water's energy level increase. Now, if the total mass of 11.5 kilograms falls 1.3 meters and all of the mechanical energy is converted to internal energy, by how much internal energy of the water will increase? Assume that there is no energy transferred from the heat out of the surroundings to the vessel and from the surroundings to the interior. So let's start with each and every part here. So let's write down the data here. So it says that you have a mass of 11.5 kg falling a height of 1.3 meters. So the mass m is 11.5 kilograms. It falls a height of 1.3 meters, and we know that gravitation is 9.81 meter per second square. So we are trying to calculate the change in the internal energy. So first things to know, so we need to know delta U here. So we know that from the conservation of energy equation, which is delta PE plus delta KE plus delta U equals 0. So delta PE can be written, so delta U becomes minus delta PE minus delta KE. So which is going to be minus of delta PE can be written as final kinetic potential energy minus the initial potential energy minus of delta KE is going to be the final kinetic energy minus the initial kinetic energy. Now, taking into consideration this data now, so notice that all of the mechanical energy is being converted to internal energy, and it only says that there is movement rotationally due to the falling masses. So which means here the final kinetic energy is going to be mgh. The final kinetic energy is going to be 0. The initial kinetic energy is going to be mgh. The final kinetic energy, potential energy is going to be 0, and initial potential energy is mgh. Final potential kinetic energy is 0, and the initial kinetic energy is also going to be 0 because there is no movement due to the velocity. Now, let's calculate the initial kinetic energy from this equation. So delta U can be written as minus of 0 minus mgh minus of 0 minus 0. So we can write that minus of minus mgh, which is going to be equal to mgh. So m here is 11.5 times 1.3 times 9.81. So which is going to give you a value of delta U, which is equal to 150 joules. So this is the total change in kinetic energy. So the total change in the internal energy. So this is the total change in internal energy. This is how you can solve the problem. So with that, we end the topic of defining. So let's move on to section 3. So in this, we're going to talk about changes in temperature and phase. So you're going to perform calculations with specific heat capacity, interpret various sections of a heating coil. So let's start with specific heat capacity. So the specific heat capacity of a substance is defined as the energy required to change the temperature of 1 kilogram of a substance by 1 degree centigrade. Now, every substance generally has a unique specific heat capacity, and this value tells you how much the temperature of a given mass will increase or decrease based on how much energy is added or removed as heat. And this value Cp is measured as, so specific heat here is measured as Cp equals Q over m times delta T. So where Q refers to the energy transferred to the substance, m is the mass, and delta T is the change in temperature. And notice that the subscript P here indicates that the specific heat capacity is measured at constant pressure. So all specific heat capacities generally are not measured at constant pressure. Some are measured at constant volume as well. But the main one that we are concerned with is the specific heat at constant pressure. Now, because there is a change in temperature, we can either use Celsius or Kelvin. We do not need to directly convert any temperatures because change in temperature has the same value in both Celsius and Kelvin. But do not use Fahrenheit. If there is a Fahrenheit temperature, convert it either into Kelvin or degree centigrade. So these are some of the values of specific heat capacities of different substances. You have aluminum, which has about 8.99 times 10 square. And one of the values that has the highest, is for water. Notice that the value is 4.186 times 10 to the power 3. So which is one of the highest amounts of specific heat for any known substances. And the second highest is steam, which is 202.01 times 10 cube joule per kg degree centigrade. So joule per kg degree centigrade is the SI unit for specific heat capacity. Next, let's talk about calorimetry. So calorimetry is the science that is used to determine specific heat capacity. So it's an experimental procedure that involves, you have an insulated container and a thermometer and a stirrer, and you have a lid with water inside it, and you're using it to make sure that one type of energy is transferred from one substance to the another substance, and calculating the changes in temperature to that of water, resulting in final calculations of the value. So this is a simple construction where we have a test substance at a certain temperature, the one that needs to be calculated for specific heat. You have an inner container and an insulator outer container. You have a stirrer to make sure that the temperature is uniformly distributed throughout the entire liquid. You have a thermometer and you have a lid that covers the outside, and you have water inside it. So the idea or the principle on which this works is simply that the energy lost by the solid is equal to the energy gained by water. So which means that Q lost of the solid must be equal to Q gained by water. So because the energy is lost here, so we can write this as minus Qs. So we know that Cp is Q by M delta T. So from this we can write that Q becomes Cm times Cp delta T. So this can be written as, so let's say we have M S Cps times delta Ts equals Qw, which is going to be Mw Cpw times delta Tw. So the one that we know here is, we know Cpw is constant, which is going to be 4186 joule per kg degree centigrade. The one that we are trying to calculate is Cps of the solid, which is generally calculated from the formula. So we can write that Cps is Mw Cpw delta Tw by negative Ms times delta Ts. So this is the formula for calculating the specific heat of a solid. So let's take the example here and let's calculate the actual value of a particular solid. So what is given here? So let's try to solve a problem here. A 0.050 kg metal bolt is heated to an unknown initial temperature. It is then dropped into a calorimeter containing 0.15 kg of water with an initial temperature of 25 degrees centigrade. The bolt and the water then reach a final temperature of 25 degrees centigrade. If the metal has a specific heat of 899 joule per kilogram degree centigrade, find the initial temperature of the metal. So let's write down the data. So the mass of the bolt, so the solid and water. So we have to calculate Ms, we have Cps, we have initial temperature of the solid, and we don't know the initial temperature of the solid, but we have the other data. So we have Mw, Cpw, initial temperature of the water, and the final temperature of the water. Remember that in calorimetry, the final temperature of the solid must always be equal to the final temperature of the water. This is the only point where we say that they reach thermal equilibrium. So let's write down the data. So that data we have 0.05 degrees centigrade is bolted into an unknown initial temperature. So it's heated to an unknown initial temperature. Then it is dropped into a calorimeter containing 0.15 kilograms of water. So 0.15 kilograms of water. The bolt has 0.050 kilograms of, So 0.05 is 0.05 kilograms of the bolt, and the CPS is given as 899 joule per kg degree centigrade. The CW is 4186 joule per kg degree centigrade. The initial temperature of the water is 21 degree centigrade, and the final temperature of the solid and the water is 25 degree centigrade. So from this we also know the formula. So we know that negative EMS CPS delta TS equals to EMW CPW times delta TW. So minus EMS is 0.05 times 899 times the initial temperature is not known, so let's consider it as TIS. So the delta T temperature is TF minus TS, so TF is going to be 25 minus TIS equals MW is 0.15 times CPW is 4186 times change in temperature is 25 minus 21. So we have 25 minus TIS equals 0.15 times 4186 times 4 over minus 0.05 times 899. So finally when you solve this, so TIS equals 25 plus, so this 25 is plus 25, so move TS this side and put this entire equation on this side, so it becomes 25 minus of minus 0.15 times 4186 times 4 over 0.05 times 899. So it will become 25 plus 0.15 times 4186 times 4 over 0.05 times 899. So this one final calculation gives you a temperature of 81 degrees centigrade. So this is the initial temperature of the bolt. So this is how you can use calorimetry to calculate unknown values. So next, finally, let's talk about the final topic, latent heat. So whenever substances melt, freeze or boil or condense or sublime, so the energy added or removed changes the internal energy of the substance without changing the substance's temperature. So that heat, these changes are generally in matter called as phase changes, and the energy per unit mass added or removed during a phase change is generally called as latent heat, generally abbreviated using L. So we write during that phase change the amount of heat transfer Q can be written as ML, where M here represents the mass and L here represents the latent heat. So let's take an example. So let's say we have water starting at a temperature of, let's say, negative 20 degrees centigrade. So when you draw the heating curve of water, let's say for example we are trying to heat this water constantly and at constant pressure. So let's say the water increases its temperature, and at a certain point it flatlines, and then again at a certain point it increases its temperature until a certain temperature, and after that point again it reaches a constant phase, and again finally starts going upward. Now let's look at these temperatures actually, and let's look at what their temperatures are. So the temperature at which it flatlines here, that temperature here is going to be 0 degrees centigrade, and this temperature at which it flatlines again, that temperature is 100 degrees centigrade. So until a certain point you have heat that is being added, so you're basically adding heat as you go along, but the type of heat that is being added is much different. So let's look at the temperature at this particular phase. So in this particular phase, there is a constant increase in temperature with the constant increase in energy. So this is the amount of energy curve. Now, as you increase energy, you're starting noticing that there is an increase in the temperature. This here is the specific heat part of the curve. So where the temperature increase is caused due to the energy increase. So the more energy is being supplied, the more the temperature increases. And you reach a certain point where you notice that there is no change in temperature, but the energy is being consumed. So there is this amount of energy that's being consumed, but there is no change in the temperature. This particular phase where you notice flatlining is called as the phase change. So this point here is called as the phase change. So what phase is changing here? At this point it was ice, and until this point it's ice, and at the end point it becomes water. So what you get here in the middle is a ice plus water mixture. So what is happening at this point here is that until here these are solid molecules. Now these solid molecules are absorbing energy, and some of the molecules are becoming liquid. So at this point it becomes a liquid solid mixture. And again, once you get across that particular point, you start noticing that again there is a constant increase in the temperature with increase in energy. This temperature again, it continuously is going to be water, and until it reaches this point, it's going to be a liquid. What happens again at this point here, it becomes vapor. Crossing that point, it becomes vapor. But again, notice that you have a constant phase curve again, where there is an increase in energy, but there is no change in the temperature. So this here is going to be a liquid vapor mixture. So liquid vapor mixture, and here you have ice water mixture and liquid vapor mixture. So this point here is the point, or this phase is the melting phase. This phase here is the boiling phase. So where it's boiling from lower temperature to a high temperature and continuously changing from a liquid to a vapor. So it starts as a liquid here at this extreme point. It's still a liquid at 100 degrees centigrade, and it becomes vapor at this temperature. So what is happening here is that the liquid molecules are gaining more and more energy and start to evaporate, and that evaporation results in vapor formation. And at a certain point it requires a lot of energy, and at a certain point it consumes all that energy and becomes completely vapor. So this here is the understanding behind the phase change. Now we talked about latent heat here. So at this phase and at this phase, the amount of heat can be calculated as Q equals mCp W delta T. That's not a big problem. But the question is, how do you calculate the amount of heat taken during the melting phase and the boiling phase? So during the melting phase, which is going to be written as QF, we can write it as M times LF. So where LF here is called as the latent heat of fusion. And we can write the other phase as QB or QV, which can be written as MLV, where LV here is the latent heat of vaporization. So which is going to be the latent heat of vaporization. So these are the two values that are used to determine the amount of heat during a phase change. So remember that this heat specifically is only calculated during a phase change. The main reason we do this is because there is no change in temperature. So there is no change in temperature. So how do you know that a particular substance has reached a phase change? Is that you notice that there is a continuous intake of heat with no change in the temperature. That point where we can consider that is to be under phase change. So these are the two cases where we will see phase change in water. So these are the two phases where you see phase change in water. So this here is the idea behind the topic of latent heat during melting and during vaporization. So with that, we end the topic on heat. I'll see you all.